Hello and welcome to today's video. We will focus on the dynamics of innovation. More specifically, the evolution of technology over time and with effort, and I will present you a model of the technology cycle. Throughout the video, concepts will be linked to real-life examples to facilitate your understanding. Let's start with Mercedes-Benz. Isn't it remarkable how they evolved from the first car with an internal combustion engine in 1885 to their latest model that can drive by itself? How can you think about this transition over time? How does innovation work when we take a long-term perspective? Now, let's take another example. Here's an artificial intelligence technology that plays the Chinese board game Go. You can think of Go as a very complicated version of chess. In this case, the time frame we're looking at is much shorter than in the previous example of Mercedes-Benz. Here we're only looking at 40 days, rather than more than 100 years. On the y-axis you can see a measure of performance. The blue curve shows you how a new algorithm performs as it learns to play the game. You see how quickly it improves over time. The dotted lines give you a reference of the performance of previous algorithms. These are already good enough to consistently beat human grandmasters. Learning is very quick. It takes less than 5 days to beat the first generation and about 20 days to beat the second generation. So how does this work? Is it just better technology in terms of software? Is it that the engineers have better ideas regarding the design of algorithms? Or does it have to do with the hardware that the algorithms are running on? Let's have a quick look at hardware. On the y-axis, you can see the power consumption, which measures the cost or the efficiency of the hardware. On the x-axis, you have different algorithms, ordered by generation. Power consumption decreases and at the same time, performance increases. What do we have in mind when we talk about the dynamics of innovation? It could be both. A very long-run perspective, as in the example of cars, but also a very short-term perspective, as in the example of AI that focuses on a narrow problem. As you will see today, the strategic aspects of technology evolution are surprisingly similar. Now, let's see how we can make sense of this more generally. Here's another plot. On the y-axis, you can see the performance of artificial hearts, and on the x-axis, you can find investment in R&D over time. As you can see, the more effort is put into R&D, the better the artificial hearts perform. The main takeaway is that the relationship between technology investments and product performance is not static. It evolves over time and increases with effort. It is also interesting to point out that early progress is slow. Then it rapidly accelerates and finally it slows down again when it hits diminishing returns. As it turns out, this is fairly general. Technology evolution very often follows the same pattern, an S-shaped curve. We should never evaluate a technology only based on its current performance. We should rather try to figure out where the technology is positioned on the S-curve to reflect on its past performance or predict its future performance. It is useful to think of technological innovation as ongoing and evolving over time to make sense of its performance. A couple more examples. Look at the evolution of tires. Again, on the y-axis you have performance and on the x-axis you have R&D effort. You can see the various technologies used: rayon, nylon and polyester. All the different kinds of materials follow a S-curve. Here are battery technologies. Again, similar axis as seen before. We can observe the same pattern regarding the growth of performance. Slow at the beginning, then acceleration, and finally performance hits a plateau. S-curves are even more general. We do not only find them with respect to investments in the development of technologies, but also with respect to investments in the adoption of technologies. Here the x-axis represents time and the y-axis shows the percentage of households that adopt a given technology. Again, we see very similar patterns of progress between various technologies, such as the telephone, TV, computers, and so on. One interesting thing is that for technologies that arrived more recently, starting from the 1970s or so, the entire S-curve seems to be squeezed into a shorter time frame. Let's see how we can use the framework of S-curves when trying to evaluate the future potential of a technology. Let's get back to AI, but this time not in a specific setting, such as playing Go, but now I want you to envision a general artificial intelligence that can take up on any task. Time is on the y-axis, perhaps depicting a few hundred years. Intelligence level is on the x-axis. The black line represents human intelligence and is our reference point. The black line slightly increases over time. Indeed, humans have become smarter over time and may continue to do so in the future. In addition, we see two scenarios representing machine intelligence. The scenario in red is where machine intelligence increases faster than human intelligence, but never outperforms humans. Then there's another scenario, the blue one, where at some point the machines become smarter than humans. In much of the public debate, the world seems divided between people believing in scenario 1 and people favoring scenario 2. But what is often missing in these discussions is what we know about technology evolution, meaning the S-shaped patterns. If we were to extend the blue curve, maybe we would be able to see stabilization and flattening. The same reasoning goes for the red scenario. It is also an S-curve, but really cramped together. Therefore, using the framework of S-curves, it seems unlikely that AI has unlimited exponential growth, since this would be very uncommon compared to many other technologies that we have seen in history. Let's now think about discontinuities in S-curves. It is usually the case that S-curves appear in pairs and that each curve represents a different underlying technical approach. To illustrate, you can think of the blue one as the next generation of the red technology. Say there's a performance advance in a blue curve compared to the red one. Now, the managerial problem is to figure out whether you want to jump to the next S-curve, meaning to adopt the new technology, or if you want to stay on the current one. Of course, this will depend on where you are located on the curve. There's always a trade-off between a decrease in technological performance and waiting until you can gain back the same level of performance with a new technology. You either give up on future technological improvements in the long run when you stay, or you give up on technological performance in the short run when you switch. This is not only true from a firm perspective, but also from a consumer perspective. In our daily life, we often take similar decisions. Do I go for the new technology right away as an early adopter? Or do I wait until more people have used it and firms have improved the technology? Therefore, changing S-curves needs to be justified as to if, when, and how to do it, thus anticipating the required changes in strategy, product, and organization. This sounds way easier than it is in practice. How do you know how your technology curve looks like? How do you know where you are located on it? How can you quantify its inflection point? Meaning, how do you determine the exact shape of the S? Now I'm going to walk you through a model of the technology cycle and pin down the different stages a technology goes through. The first stage is called fermentation. Here you have a competitive evolution where different firms propose different solutions to a market problem, and then these different solutions substitute each other. Therefore, the technological change is led by the community. The second stage is a selection phase, where dominant design gets established. It is the outcome of the first stage. The third stage is renovation, where we get incremental improvements, such as a focus on the process, improvements of the dominant design, and where we get technological momentum. Finally, the fourth stage is variation, where there's a technological discontinuity that leads to a new technology. This stage is illustrated with jumping from one S-curve to another. As a result, the cycle is completed, and with the new technology begins another cycle. Let's deep dive into the 4 stages. You can think of the fermentation stage as a number of variations of the new technology occurring on the market. Early ideas, called prototypes, are usually crude and experimental when first introduced. The new technology is not well understood yet, and each company is aiming to differ from its competitors. The competition is on who is the best at solving a problem. Also, it's interesting to point out that old technologies do not just vanish from the market. They are rather stretched to their limits by users. The era of ferment ends with the emergence of a dominant design. Here's an example of a dominant design in smartphones. On the x-axis I depict time, and there are 2 y-axes. The first one representing the percentage with a dark line, and the second one representing some measure of performance. You can clearly see a dominant design emerging. The share of smartphones with a multi-touch screen, a technology that was first introduced with the iPhone, increases. At the end of our time axis, every other smartphone looks like an iPhone. Now, looking at the second y-axis, we can see that there is a spread in the distribution of computing power in 2005 that looks quite similar to the one in 2013. This means that there are both slow and fast smartphones in all years. Thus, although we have a dominant design, there are clear differences in terms of performance. Now, where does dominant design come from? It is usually a combination of market demand, technological possibilities, and individual, organizational, and governmental factors. It is important to mention that companies push their own design via licensing, for instance, to become the dominant one. Another way to think about it is that the market operates with packages of well-established innovations in favor of technical excellence to reduce technical uncertainty. So having a dominant design is good because it reduces the uncertainty. But this does not mean that the dominant design is always at the frontier of technological performance. So why is dominant design important? Well, it reduces experimentation and establishes clear performance targets. From a producer's point of view, it permits companies to design standardized and interchangeable parts to optimize organizational processes, volumes, and efficiency. This is a prerequisite to mass adoption and volume production. Finally, from a customer's point of view, it reduces product class confusion and decreases prices. Moving on to the incremental change phase, after the dominant design arises, technological progress comes from numerous incremental improvements of the dominant design, instead of trying to invent completely new stuff. In addition, the technological regime becomes more orderly, since more firms are focusing their efforts in trying to improve the dominant design. Most performance improvements over the entire lifetime of the technology will occur outside the era of incremental change. Finally, the focus of competition shifts from higher performance to lower costs and differentiation via minor design variations and strategic positioning tactics. The evolution of the iPhone across generations is a great way to illustrate incremental change. The main functions remain the same. Only relatively minor things change. They make edges round and then sharp again, and they add cameras here and there. To sum up, in this video we talked about how technologies evolve and the patterns this process follows in the short and in the long term. We've also seen a model representing the technology lifecycle.